In this video, I will try to introduce you to the assembly line balancing topic, which is really very important for operations management. I will provide a couple of illustrative examples, and I think that they will be more than enough in order to assist you in working with problems about line balancing. So let's begin by setting the framework. When we're talking about assembly line, what we have usually is a production line which is organized around some tasks. The tasks take time in order to be performed, and usually we have some people or some machines allocated to every task. So usually we talk about the workstations, which is the way that we deal with the various tasks. So each workstation performs a number of tasks. It could be one task or more. What we try to achieve by organizing or line balancing our assembly line is to assign the tasks to each workstation so as each one works more or less equally in terms of time. And the second goal is to maximize the efficiency and minimize the idle time for each of the workstations. Let's begin with a very simple example to introduce the basic notions around line balancing. Suppose that we have a facility that produces frozen pizzas to deliver to supermarkets. You can imagine roughly what the required tasks are about this facility in order to produce a frozen pizza. So a manager should first of all identify what are the necessary tasks and break them down into a table similar to this one. So you can see here to the left side the tasks that have to be performed in order to produce one unit, one frozen pizza, and then you have to more or less identify or calculate somehow the time that is required for each task to be completed. So for example, you can see here that we have to select first of all the dough, which takes 20 seconds, press it to take the shape, then have an inspection whether it is appropriate or not. So if it's not, then reject that. Then a quick bake to get a solid form, then add tomato sauce, cheese, toppings, inspect if everything is fine, and then package and send it to a supermarket or to the freeze. So if we sum all those tasks, we will have the sum of task times, which is defined as the total time of all the tasks in order to create one unit of this product. So in our case, is 291 seconds. So this is important because it will give us, let's say, the base in order to find out later on the cycle time and the number of workstations that are being required. So, as we said, the activities here are presented in this table. As you can imagine, the whole set of tasks cannot be performed in a parallel way, which means that if I have let's say, if I have in my hands the tomato sauce, I cannot do something with that unless the previous step, which is the fast baking, has been over, or I cannot bake the dough if I have not before shaped that or selected that. And of course, I cannot package that if all the previous steps are complete. If the previous steps are not complete, then I cannot proceed to the next one. So the way that I depict all those steps here is what we say the precedence diagram. And as you can see here, everyone follows more or less a sequential flow, and it is indicative for this type of production line. Some other production lines might allow us to perform some tasks into a parallel way, but let's focus in this case here. Again, as we can see on the top right hand, the sum of the task times is 291 seconds. From this precedence diagram, we can visualize this table and make the whole line more intuitive. So what we want to achieve here is to find out some variations that might increase our production rate or increase the efficiency. So let's check a couple of variations on the way we approach our line. So the first question is, if I have only one person or one workstation that undertakes all the set of tasks, can you tell me, can you imagine how much time it will take to deliver one pizza from this line? Is it going to be 50 seconds, 100 seconds? What do you think? Well, if you think a little bit, you will see that whenever some material is being introduced here at the beginning of the line, it takes, as we said, 291 seconds to reach the end. So the cycle time, as we define it, which is the output rate of our line, is 291 seconds, which means that if one person here undertakes the entire set of tasks, then one pizza, one product, one unit is going to be produced from this line, from this setting, within 291 seconds. And this is what we call the cycle time of our line. Now, as soon as we define the cycle time, which is the output rate of our line, we can define the efficiency as a percentage, which is actually a fraction where we divide the sum of the tasks time, which is 291 here, over the workstations times the cycle time. In our case, we have one workstation because, as we said, we assigned all the tasks to one person. And as we said, the cycle time is 291. So the fraction is equal to 1. So our efficiency is 100%. Well, it might sound a little bit weird, but if we combine that with the idle time, which is actually the time that one person or one workstation remains idle by doing nothing, then you can understand that the efficiency and idle time show us how much time we actually miss. I don't want to say we waste, but we do not utilize. So when the efficiency is 100%, we utilize the 100% of our resources. If the efficiency goes lower, 80, 70, then this means that we have idle time, which means that we don't utilize the full, let's say, the full capability of our resources, either it be some person, some employee, or some robot, some machine. So if we count now, okay, given those cycle time and the setting here, what is the actual output rate, which means how many pizzas do we produce per 1 hour? So we divide 1 hour, which is 3,600 seconds, over this sum of the task times, and we get the result here, which says that we can deliver, by using this setting, 12.4 pizzas per 1 hour. Well, that's a number that we can keep. One manager might think a little bit and ask whether we could achieve something better. It could be, let's say, a higher output rate, for example. So let's ask the question, if we have two persons, if we engage two persons or two workstations to perform the tasks somehow, can we get something better than the previous one? So let's try one different setting. Suppose that we split the tasks here into two groups, and we assign those tasks to two different people or two different workstations. The first one, to the left, the first group, adds up to 180 seconds, and the right group adds up to 111 seconds. So we have here two groups of tasks, two workstations perform those tasks, and if we calculate now the cycle time, you will see that, as we said, it is the output rate of the line. Now, the output rate of the line here is 180 seconds. And why is this so? Well, think a little bit that if we are talking about a continuous flow of pizzas, okay, continuous flow, then the first person begins here at 0 and finishes after 180 seconds. And then it passes this let's say, prepared pizza to the second person. But as soon as he passes the pizza here, he begins a new one. So his cycle is 180. So this person, every 180 seconds, delivers a pizza. As you can see here, the second group is 111. So the second person is able to catch up this rate. So as you can see, two people working at the same assembly line can deliver a pizza in 180 seconds. And this is our cycle time here. Now, if we calculate the efficiency of this setting, if you do the calculations, you will find that it is 80%. And the idle time here is 69 seconds. Why do we have idle time now? Because, as we said, the first person is working 180 seconds, but the second one only 111, which means that for the 69 seconds that the first person is actually working, the second one is just sitting, waiting for the first person to complete the pizza. So this is the idle time. Now, if we want for this setting to calculate again the actual output rate, how many pizzas do we produce per hour, we find that we can achieve with that setting 20 pizzas per hour. Of course, the manager might not be so happy with that and might try to figure out another setting, more, let's say, more efficient, more productive, with a higher output rate. So another question that could be asked is, what if we could employ 4 persons or 4 workstations in order to perform the task and try to figure out if we have a better output rate? So let's figure out if we can do something like that. Now, if we split the tasks into 4 workstations, we could probably do something like that. It is one from the many possible arrangements. We have to figure out here that the fast bake task requires 95 seconds, which is pretty high, and it is the highest duration of all those tasks. So we can not avoid to keep this task as a single task assigned to one workstation, and figure out whether we can group the rest of the tasks in a way that they do not exceed or they're around 95. So if we try, give a try with a calculator, because this is a simple example, we can identify that if we group the first 3 tasks, we have 63 seconds. If we group the sauce and cheese, we get 44, and the 3 at the end, we get 90. Of course, we have to be aware that we need to consider the sequential flow. So, assuming that we have this setting here, if we calculate again the cycle time, we can see that we can deliver one pizza within 95 seconds, because 95 is the actual output rate of our line. And why is this so? Because, as we said before, every 95 seconds, one pizza is being delivered from the beginning to the end of our line. And 95 is being actually defined by the highest, the task that has the highest duration. If we again calculate the efficiency, we see that it is 76.5%, which is a little bit lower than the previous one. The idle time here is 89 seconds, which is again a little bit lower than previous, but in this setting, what we have achieved is to get more than the previous output rate at a large percentage. Now we can deliver 37 pitches per hour. One problem here that the manager has to consider is that here we get a higher output rate, but we engage more resources. So there is a trade-off between those things, and of course there is not only one solution, but depends on the aims that every production facility considers. So if we want to define in a formal way the cycle time, we would use this formula. The cycle time is actually defined as the available production time divided by required output in units. And as we said, it indicates the time it takes to produce one item, one unit from the line, and defines the output rate. So the more units we want to produce, the less time we need here as a cycle time. The less time our product has to spend at its workstation. And this is the cycle time. Well, given the cycle, we can find the minimum theoretical number of stations by using this fraction. So if we divide the sum of the task times, that is something that we already know, by the cycle time, we get the number of workstations that theoretically solve our problem. Always, as soon as we find a decimal number, we round up. So we said that we're talking about theoretical, not actual, because in practice we have some constraints that might lead us to a larger number of workstations in practice. And two indices that we use in order to find out whether our setup is efficient or not, and what is the idle time that we will face in this setting. So the line efficiency is actually in percentage, is actually the fraction of the sum of task times divided by the actual number of workstations times the cycle time. And the idle time is the difference between the actual number of workstations times the cycle time and taking out the sum of task times. Now, those numbers are quite useful when we want to reach out to a conclusion for our line balancing problem. So if we go back to our problem, as we said, in this case, we have 4 workstations. Probably it's not the ideal efficiency, or we cannot reach 0 idle time at any possible setting here, because we have to consider that there is a task that cannot be broken down further. So we need to consider that. So if we're happy with the output rate, then we can keep it, but we also have to consider the cost that we will have by engaging 4 different workstations. So that was a simple example where all the tasks were actually following as you can see here, a sequential flow. Now let's move to an example that we have some precedence. Suppose that a company, ABC, assembles some products on a production line, and we have identified here 9 activities where each one might have a preceding activity or not. And we have also identified the time it takes for its task to be completed. So, as you can see here, the table shows us a lot of information, and the objective is to produce 35 units per hour, and we know that every hour, every working hour, is actually the productive time is 60 minutes. So the next step is to Of course, as we said, the total, if we add all those times, we get the sum of task times, which is 291. And the next step is to design the precedence diagram to identify how we will assign the tasks into workstations. So in this case, I have designed the precedence diagram following the table. So as you can see, A and D tasks have no preceding activity, so that's why they're sitting here alone, standalone, while B has A as preceding, C has B as preceding, E and F have both the C as preceding activity, and so on. So I, at the end here, has EF, H as preceding activities. So if we design this precedence diagram, it will be very helpful for us to identify, visually, the way we allocate, we assign tasks to workstations. So the goal here is to achieve that production per hour, 35 units per hour. So let's proceed then and try to identify how many workstations do we need in this setting, in this line. So first thing, find cycle time. If we follow the formula, as we said before, then the cycle time is the fraction of between time that we have available by units divided by the units. So we have 35 units into 1 hour. If we reverse that, we have 60 minutes divided by 35 units, which gives us 103 seconds per unit. If we take this result, we can find out the theoretical minimum number of workstations, which is the sum of the time for all the tasks, which is 291, divided by the cycle time we have just found before, which is 103. So we take 2.82, which rounds up to 3. So what we're looking for is to assign those tasks, to group them into 3 workstations. So one possible solution that I'm going to show you, because we of course there is no one solution, we might have a large number of solutions, especially when the number of tasks is quite large. So let's begin by saying that we want to achieve what? To group those activities, those tasks, into 3 workstations, but every workstation should roughly be below 103. Okay, so that would be the most efficient solution. So going to the precedence diagram, we see that we have this task which counts for 95 seconds. So we cannot group this task with any other task here, as we can see, because it will exceed the 103 seconds. So we keep it as a standalone, and this one is going to be 1 workstation. Next, we try one way to approach that is try to find the next let's say the next task that has the highest duration, excluding that one, because we have allocated that. So the next one is 64. So we would like to group 64 with some other tasks. So we can here, it's a kind of try and error. So we can use a calculator or try to figure out what's the best way to approach that. So if we trial it a bit, we can figure out that if we add those 3 tasks, we can get a 95 duration, which is quite decent for our case. We don't break here, we don't violate any restriction, any constraint regarding the precedence diagram, because one person can do C, F, and G, because everything will be fine and everything will be ready. So we have another workstation left to use, so we would like to avoid using a fourth workstation. So let's see whether we can group all the rest tasks into 1 and can achieve something. Yeah, so we see that we achieve 101 seconds, which is quite close to our theoretical cycle time. As we can see, there is no problem for one person to perform A, B, and then E, I, A, H. And of course, it might look like a little bit weird here, but imagine that we are sitting at a facility that we can arrange, let's say, the assembly line in every way that fits our purpose. So if we find our efficiency level and idle time for this setting, we see that the efficiency level is 94% and the idle time is 18 seconds, which is quite effective. I mean, we see that we have reached a high level of efficiency. Idle time is quite low, which means that we utilize our resources, let's say, almost at the maximum. And of course, we can we can calculate what is the actual output rate by using this setting. It's a little bit more than 35. And why is that happening? Because as you can see here, the theoretical cycle time is 103, but in reality, we have 101 seconds as our cycle time. So we have a benefit, we have gained 2 seconds from the theoretical. Well, in reality, of course, ideal situations are rare, so we have to count for some breaks. So we have to not to look for 100% efficiency, but a little bit lower, because in real life, any type of problems might happen. So we have to provide some buffers to our operations. So I hope that you found this example quite intuitive to give you a well understanding of how we work on line balancing problems. Thank you very much. Bye-bye.